that's up focused as well.
Nothing is uncrackable. It's just whether it's worth it or not.
There's a point of effort and gain.
Yes. But then there are obsessions too.
Yeah, definitely.
All right. So the recorder is on. I am currently recording. Okay, so I will go ahead and get started. How many people finished the whole thing? Feeling pretty good about it. Okay, so a few people did not manage to finish it. So what I'll do is I'm going to give these people maybe a second chance to turn it in, but at a discount. Okay, so instead of turning in something that does not work, I want everybody to turn in something that does work, but it will be a reduced point value, but still it's better than nothing. So that's what I'll do. Is you guys can still turn it in late, okay? Which also means I cannot talk about the solution tonight. I mean that's. So I cannot talk about the solution tonight. I'll give you guys an extension of maybe 2 days. That should be fine. So Saturday evening, would be the due date. Like a hard deadline, that would be like the day when I say, that's the cutoff. But if people who turn in today, if you turn in something today and it's not working 100%, you kind of have to gauge, whether to turn it in again, but turn in something that works 100%, or whether just to leave it like the way it is. Okay. I would, turn in something that does work. Okay, I think that's probably advantageous. All right. So are there any questions? So that kind of blew, a part of my original plan for tonight, which is to talk about the solution of the homework assignment. Okay, for those of you who did finish the whole thing, what was the most challenging part of the homework assignment?
Yeah, I thought
the what? The last one?
The last one was first. The last instruction. The last instruction. Just wrapping your head around the whole thing.
Well, that was part of the reason why that was the instructions is for you guys to
Make a diagram. You can see exactly what goes to
and
what.
because of the score
And it's really
instruction is
simple.
already
see, I put it in backwards the first time.
So that means you can kind of look into that one and go like, okay, it's already doing something, it's exercising about the same components. Then you can take a look at that and like, okay, how should I modify that to do exactly what I wanted to do? Okay, so that's a good move. Just to look at existing code and see how it's done. Good job. All right. So just to say it one more time, if you have turned it in already, that's good. If you know that it works, that's it. Okay, don't do anything about it. If you turn in something that is not working 100%, or you have not turned it in yet, I'm giving the whole class an extension of 2 days to turn it in. So Saturday is going to be the hard deadline. That's like there'll be no submission after Saturday. But if you turn in late, there will be a deduction. I still have to kind of think about the percentage, but it's still going to be worth it to turn it in late as opposed to not turning in or turning in something that does not work. Because the way I grade is, if something does not work, it's really hard for me to get to give out partial credits. So it's probably a good idea to spend the extra 2 days, get it working, and turn it in. Which, from the other perspective of instruction, it's actually what I want you guys to do. I don't want my intention is not to give people a low grade or to have people not turn in the homework assignment. I want everybody to be able to do the homework assignment, learn what is involved in the homework assignment, and turn it in, get all the points, and have good grades. I don't have a problem with the entire class getting A's out of this class. I do not grade by curve. But once you move on to a 4-year university, some professors do grade on curve. And what does that mean? Yep.
It's like wherever the majority of students land, they make that the C.
They use percentage. Exactly. Okay. They use a percentage to decide. Okay. Out of the whole class, only 5, 6, whatever number, whatever percentage is going to be A students. So it doesn't matter if you have an entire class, filled with geniuses, genii, plural of genius. They will only let 6% of those people to get the grade of A. and maybe 15% of A to get a B. And then as far as C, D, and F are concerned, probably they'll just be based on actual grade. But that is kind of unhealthy in many ways because let's say you're a pretty good student, okay? You got everything done already. Would you help another student in a class like this, the way it is right now? No, right now.
Yeah.
In this class, where it is absolute, right? The threshold is absolute.
Yeah, no.
But in a competitive environment, you may reconsider, right? You may not go to the extreme of poisoning somebody else's project or telling somebody misinformation, but to spend your extra time to help someone else, it's something now the balance is shifting a little bit. Okay? So I don't want to have that type of atmosphere in my class. I want you guys, if you have time, you can help out another student. Now, of course, there's the question of how to help out another student. Just giving somebody else your answer is not going to be very helpful. So I will leave that up to you guys to kind of decide, what is the best way to help out another student. So I can't really talk about the solution tonight because I'm giving the whole class an extension. But instead, I still have more stuff that I can talk about, and that's the practice exam. Yay! Yeah, some of these questions are pretty easy. Question number 1. Identify this schematic and label the pins accordingly. In other words, tell me what it is and tell me what the pins are. Label the pins. That's pretty easy, right?
That was the first thing I thought.
That's a what is it?
Well, it was an XO.
No, as a whole thing, as a whole.
Oh, so
Okay, here. It's a half adder, right? So the top 2 pins are the input pins. Okay, the 2 bits that you're adding. The bit on the left-hand side is the carry bit, and then the bit at the lower part is the output or the result. Okay, so if you use any one of those terms, you'll be fine. Okay, cool. So question number 1 is pretty easy. Question number 2. Question number 2 is slightly tricky. Okay, it is slightly tricky because some people will not read the entire question and say it's a full adder and then label the pins and then I'm done. Well, but it can also be a full subtractor. Okay. Now the previous diagram has to be a half adder. There's no way it can be a half subtractor because the way the gates are arranged. But this one can easily be a full subtractor because I did not label the subcomponent. So the subcomponent, each one can be a half adder. It can also be a half subtractor, each one of these. So you have to read the question carefully because it says right here, note that there are 2 possibilities. Identify both schematics. So you have to say it can be a full adder, can be a full subtractor, okay? And label the pins for each schematic. And then I make it even more clear down here and say, yep.
No, go ahead.
Okay, so this part, is really a big, huge clue. This is particularly important if the pins are not symmetric, okay? Because when you're dealing with an adder, the pins are symmetric. The input pins are symmetric. But when you're dealing with a subtractor, the input pins are not symmetric. So in that case, you have to identify which pin is being subtracted from which other bit. But I cannot spell it out because if I spelled it out, then you guys would know, oh, it's a half subtractor. And then half the class will forget it. It can also be a half, can also be a full adder.
So
Yep.
the question was, is there any construct where one of them would be a half adder and one of them would be a half subtractor?
No. Nope. So the way you identify which one is being subtracted from which other one is the input borrow. Yep, go ahead.
Would you, like, if we put for the adder, like we put the carry as a subtractor, we just say carry as well?
Yeah, we say carry also when we're dealing with a subtractor, just because that's going to be the convention when we deal with the actual processor. Yep.
So in the question, we're going to have the schematics, but without the X and Y and Z.
This one is labeled. Yep.
But it says label the pins accordingly.
Yes.
So the labels are going to be missing out on the test.
But no, but those are not the pins, those are the wires. The pins are the squares and the circles.
Yeah.
So that bottom circle would be the result.
Yes.
Of the whole thing, the circle.
Correct.
Not X1. Input one.
Yep.
And then,
But in the case of a subtractor, you have to identify which one is being subtracted from which other one. So you will have to tell me one way or another, and make it clear. Yep.
Can we summarize what do we need to do here for this question? I just
What
make
do
sure
we
I
have to do
understand.
here?
Yeah.
You have to identify this is the output borrow or output carry.
Uh-huh.
This is the input carry or input borrow. This is the result, but the most important part is these two. Okay, you have to identify, okay, if you label A, B, then in the result you have to say which one is subtracting from which other one. So in this case, it is Y, it's basically X minus Y. That has to be the way it is arranged because of the second half subtractor is arranged that way. Because we subtract the input borrow from the result of my own two bits. So that determines, the direction of the subtraction. So X minus Y is the result when it is a subtractor. Now when it's an adder, we don't really care because addition is commutative, so it's symmetric. Okay. Any other questions about number 2? Yep.
Just to clarify, we would put X minus Y as the result?
X minus Y as the result, that would be fine too. Yep. All right. Question number 3 is where things get a little bit slower. It will slow you down a little bit. Yay! So we have the full architecture, which is not really needed in the class. Sorry?
You're not going to change it up, are you? It will be our friend, right?
It is the same thing. It's the same as your homework assignment. Has the same. It has all the same features. I have not changed it at all. Okay. In one of your future homework assignment, you'll be changing it, but at this point, it's still exactly the same as before. It's just that I don't want you guys to say, oh, but I forgot to print it out and bring it with me, so I'll include it in the exam. So this way, it's always there. And given this is the following is the microcode in ROM, which is the stock, ROM that comes with the simulator, comes with my processor, with the exception of the first microcode of the fetch cycle. I fixed that one up instead of being 0. Now it has actually some value, but it really does not change anything. And in RAM, it's all blank. Oh, I don't have any programs written here. Well, it is a program. It's just that it's not a very meaningful program. Okay. So the question is asking. Assume that the whole architecture is reset. So assume that you just hit the reset key. Assume the clock is initially 0, which is the end result of resetting everything, and that's the initial state of the simulator. What is the state after the clock goes through the states from 0 to 1, back to 0, back to 1, back to 0, back to 1, back to 0? Note that the MCC, the microcode counter register, updates at the falling edge, okay? Because that's the only one that updates at the falling edge, not a rising edge.
that's 1 to 0. That's switch from 1 to 0.
Yeah, when the transition goes from 1 to 0, then it clocks in whatever is presented at the data point. Specifically, what are the values of the microcode counter and the program counter after this particular sequence? So you have to write down, okay, the microcode counter is going to be blah, 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 and the program counter is going to be blah, 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 blah.
So it's based on we don't have a value in RAM and in ROM. We just can clock.
No, we definitely have values in ROM and RAM. It's just that without programming it in any particular way, if I just clock, okay, if I just toggle the clock pin the way I described here, which is basically toggling 6 times because it starts with a 0 by default, so I have to clock it 6 times, I have to toggle it 6 times. So now the question is, after I clock it 6 times, what's going to happen? What will be in the program counter and what will be in the microcode counter? That's the question. Okay. Now I'm pretty sure some of you have tried that already by accident. Okay. You thought your program was loaded because you did not detach the reset pin from the clear line. You actually ended up clearing the RAM, and then you clock it and go like, oh man, this is not what I wanted. but you may not have observed the actual result of doing this. So what we need to do now is to look at the actual instructions and figure out what it is going to do. But what about the spreadsheet? The spreadsheet is not here. Well, the spreadsheet is more or less, an aid to help you get along when you're starting out with these things, but you don't really need it. What do I mean by you don't really need it? Well, look at the microcode here, okay? So the microcode is 11500. Now, how do I figure out the bit pattern from looking at just 11500? I don't have my spreadsheet. How can I figure this out? It's called hexadecimal to binary conversion. Okay. Now, if you look through this, this question here, if you go a little bit further, I guess I put it at the wrong place. I gave you the whole table. In other words, on the left-hand side, we have a hexadecimal digit. On the right-hand side, we have the 4 bits corresponding to that hexadecimal digit. So the conversion is just like that. It's table lookup. Okay. The more you use it, the quicker you get used to it and just basically memorize most, if not all, of these patterns. How many people think that you might have most of these memorized already? There you go. Okay, so it's something. It's just it just requires repetition, but you can do it. Okay. All right. So given this table, which is already provided here, what am I going to do with this microcode 11500? Okay. Now 11500, you basically look at each hexadecimal digit and convert it into 4 bits. So the 0 here, the least significant digit is 0000. There you go. Another 4 zeros, 0101, 0001, 0001. Okay? So this is how you figure out the actual bit pattern given the hexadecimal representation in the ROM. And then you count 17 bits, which basically would be this portion here. The most significant 3 bits are not really used. This is bit 0, and this is bit 16, because we count from 0. But there's a total of 17 bits. Okay? So what do you do with all these bits? Well, you look up this portion here. Exactly. You look up all the wires, and then you figure out, oh, okay, bit 0 goes from the ROM module to where, and so on. Now, but you have done this already, okay? You have already done this because you have been doing the homework assignment. So for the most part, it's the same thing, okay? So from that, you can basically identify what this is going to do. But with this question, it's a little bit easier because we know what the fetch cycle is supposed to do already. Okay, so from your experimentation when you're doing your homework assignment, what does the fetch cycle do? Those 3 microcode at location, starting at location 0 in the ROM. What do they do?
They get back instruction.
Okay.
Feed it back into the.
And then it increments the program counter. The last one, what does the last microcode do? The third one.
Resets the microcode counter.
Sorry?
Resets the microcode counter.
No, it does not do that. It decodes. It takes whatever is in the instruction register, pull the most significant 4 bits to become the most significant 4 bits of the address of the ROM, and then it will pad 4 less significant bits, to make a 8-bit number, and then that 8-bit number becomes your new MCC, the new microcode counter. What if your instruction is this? What if your instruction is 0, 0? What is the most significant 4 bits? 0. And if I pad another 0 as the least significant 4 bits, what do I end up with? 0, 0. That becomes the new MCC, the new microcode counter. Okay? And what exactly is at location 0, 0 in the ROM for the microcode? It's the same thing, the fetch cycle, right? So what does it do again? The same thing, right? It becomes repetitive. It's just like, when Pinky asked the brain, what are we going to do tonight? Same thing every night, right? So it's the same thing. So now,
How to catch instruction people?
yep. So now the question is, how many clocks or how many times do I have to toggle the clock pin to get through one microcode?
We can go back up.
The answer is 2, right? Because the 0 to 1 transition doesn't do anything with as far as the microcode counter is concerned. It does do other things, to the rest of the system, but it doesn't do anything to the microcode counter. But when it goes from 1 to 0, this is one increment or one clock to the microcode counter, and this is another one. This is the last one that will basically decode the instruction, but when the instruction 00 is decoded, it goes back to location 0. But the program counter is increased from here to here already. So if I do this all over again, okay, it's going to do what? But actually the question only has one set, right? So what it's going to do is the program counter is incremented to 0, 1, and the microcode counter is going to be back to 0, 0. That will be the answer. Okay. Are there any questions? Nope. All right. So that would be that's question number 3. And obviously, the more you are familiar with the architecture because of doing the homework assignment, the quicker you can come up with this answer. But during the test, we don't have any electronics, so you cannot really just run the simulator and clock it and figure out what it's going to do. That's the whole point. I mean, you should be able to figure this out by hand as well. Question number 4. Question number 4 is showing you the details of the register bank. It has not been changed. Okay, this is exactly the same as the processor that you're dealing with. Write a new instruction. Oh no, new microcode, right? Write a new instruction with an opcode of 1000 YY question mark, and I made it very clear this is all a binary number. In other words, YY is basically just 2 bits to specify something. And I want this instruction to store the content of the register identified by YY, which is a bit pattern, to the location in RAM pointed to by indir_reg, or the indirect register. Assume indirect register of the processor is already initialized. Okay, so this is basically a mirror of one of the instructions that we have already implemented as a part of your homework assignment. Because as a part of your homework assignment, you have a instruction called, no, it's not a copy,
It's number 4. It's byte code 4.
I think it's the LDINDIR, or load.
Yeah, which is
how did I call it?
It's up 4.
Right? Is that how I call the instruction?
Yeah.
Okay. So it's basically the reverse of this. Basically what I'm doing is store indirect, but not using one of the 4 registers for the indirect part. I'm just saying, okay, the indirect register itself is already storing the pointer of where I'm supposed to store the content. You just have to specify a register, and that's all you need to do. Okay.
Is that initializer, which means?
It has some. Assume it already has the value, already has a pointer. Okay, so here's the question. First, indicate the address in hexadecimal of the first microcode corresponding to this instruction in ROM. In other words, if I look into the ROM editor, where am I supposed to start placing my microcode? 80, exactly. 80 is the answer because the instruction has 1000 as the most significant 4 bits. That is what we use to index into the microcode ROM as the starting point of that microcode, of the sequence of microcode. Okay, 80 is the answer to this particular question, and then the next few spaces will basically give you a chance to specify the it's not the opcode. This really should be saying the microcode. So specify the microcode in hexadecimal in the following space. All right. So does everybody understand what the question is asking? It's basically a micro homework assignment, kind of like what you did or what you're still doing, depending on whether you turned it in already. Except this is only one instruction, And that one instruction is should be strangely familiar, because we have a store instruction already that I implement, and you guys implemented the load indirect already. So this is kind of like a combination of those two, but it's not going to be much more complicated than what you have done already. Okay? Are there any questions about this? No questions? Okay. So let's go ahead and figure out, what the microcode is supposed to be like. Okay. So what you need to do, the first thing you need to do is to take a look at the architecture here, and then you say, okay, so what we're doing is we are assuming the indirect register already has the address that we want to store to. Okay, that's already there. The register bank has the register that already has the value in order to store into that location. So your job is to sequence the operations so that you first specify whatever is in the indirect register, go through these mugs and specify the address to the RAM. Okay, so that's the first thing you have to do. And then you have to play with these pins here, select the RAM, change the load operation to a 0, so it becomes a store operation. And then you have to ask the register bank to output through this little buffer here onto the data bus, so that the data will be presented here. Okay, and then you wait for 1 clock cycle, because the clock is universal, and the RAM does store based on the rising edge. So that would be like the rising edge right after the falling edge to increment the microcode counter, and then you have to reset the microcode counter just like with all the other microcode sequence, and you're done. Okay. Are there any questions about what we are supposed to do using this picture? Yep.
Can we try later? How can we change the value from the RAM while they debugging? I just and next sim unlike debugging, and then we change the value and track all the output.
Okay, you want to change the value of RAM, or do you want to?
While they debugging.
While you're debugging it,
Yeah.
you can change the content of RAM anytime you want to.
Yeah, we do that.
Hmm?
Yeah, let's try it.
But I'm doing it on paper. Remember, I'm trying to do exactly what you guys have to do, which is on paper. Okay, so it might be helpful, if you want to do it, in this question, it might be helpful to kind of write down here in text first, what you're planning to do with each clock cycle, and then you use that as a basis and go, okay, now which wire is supposed to be a 1 and which wire is supposed to be a 0, and so on. Okay. All right. I will use the other. I will use LogicSim to display, but I'm not going to use it as a tool to actually run it, because it's just easier to zoom in and look at different portions. So that's what I'll do now. Let's do that. Okay.
So we can download this file. No,
Which file?
this one.
Everything is online already.
And
On
which means
Moodle.
already upload to the Moodles.
It's already on Moodle.
But the file, we can download the file, but just can't
What file?
the file you show us. That's the
It's already
word.
online. It's called the practice exam.
Control unit folder.
Yep.
Do you have the date set for that exam?
Yeah, but we can.
Uh,
there is
1
no
week
file
from
we can
today.
download.
Okay.
So it'll be next
I'm not
Thursday.
Sure if my computer reading. Yeah.
All right.
I can
So-
open, but I can.
So what we need to do is to look at all these wires, and I know it's going to be a pain to track these wires. So if you want to help, get some additional help, you might want to take the spreadsheet that I have, reformat, those, pin to number, correspondence just a little bit to make it more user-friendly. Okay? Because remember, this is an open book and open notes, type of test. So you can actually bring anything you want as long as it is either printed or handwritten prior to the test. So if you know that this type of question is going to be there already, it may not be a bad idea to prepare for that, right? Okay, you might have a little enlarged picture of the processor architecture, so it's easier for you to track all the connections. you might look at the spreadsheet. Okay, I'll just kind of show you exactly what I mean by that. Okay. So you can look at the spreadsheet, which is MCC states.ods, and because this one has all of these, names already assigned to the bits, you cannot use a spreadsheet during the test, but the names can still be helpful. In other words, it might be helpful to turn all these into a particular format so that you can easily and quickly look up which one is which one. Yep.
Wait, so we can't use the spreadsheet, but can we print out the spreadsheet?
Oh yeah, you can print it out.
Oh,
You
okay.
can make your own spreadsheet if you want to. Because if you print this one, it's going to be too wide. You have to kind of paste a few pieces of paper together. There are ways to make this more readable. You can align the text instead of making it horizontal. You can make it vertical, so that way it's more quote-unquote user-friendly. I'll show you exactly how to do it.
No, it's just you were saying we couldn't use the spreadsheet during the test, and I was like, so we can't print this out.
Yes, you can.
We can print this out, but we
Yeah,
can't.
you cannot use a spreadsheet application during the test.
The only thing
it doesn't do is convert to hexadecimal format. Yeah.
No, but these names can be helpful. Okay, so that's what I meant. Is you might want to have a little quick table to look up these names and arrange it in a certain way, because the way I arrange it in a spreadsheet is okay if you're doing all the calculations using a spreadsheet, but if you want to do the conversion like this, you want to put bit 16 to the left-hand side and bit 0 onto the right-hand side, because otherwise things are not aligned correctly and you have to go through all the extra steps to get it done by hand. So to prepare it so that you can work on this more effectively, you can do whatever tool you want, okay, as long as it's a piece of paper or it's printed or handwritten, that's fine.
I just realized that that's what that formula is doing now. It's just doing like whatever, like for when we have our ALU, that's our least significant byte. That's just 16 to the power of whatever.
Right.
Okay.
So I'm just going to show you guys how to turn the descriptions sideways. Okay. So I'll just go ahead and select like a whole bunch of these guys. Go to Format, go to Cells, and you want to turn the orientation to 90 degrees. 90. Tweak it. And then click OK. And then after this, what you can do is you can select the columns that are involved, like so. Double click the bar between the columns, and it all aligns kind of nicely. Okay? So, but they're still in the wrong order because the least significant bits are on the left-hand side and the most significant bits are on the right-hand side. So you can still kind of work on this a little bit and make it more user-friendly. Okay? And you can pre-print something like this as an aid to help you, figure out the actual, hexadecimal numbers. You can even have thicker bars at, 4-bit boundaries, so that way you can quickly identify them and go, okay, these 4 bits, become one hexadecimal digit, those 4 become another one, and so on. Yep.
Is this exam going to be on Tuesday?
Thursday. Next Thursday. So if you do have any questions, there's one more day to ask questions about the exam. Okay. So are there any other questions? Okay, if there are no other questions, I'm going to finish up, the answer of the question at hand. And what I'll do is I'm not going to rely on the automated calculation thing here, and I'll just do everything by hand. I'm just using the spreadsheet as a quick way to look up which pin is doing what, which you can also do using the schematic, but that takes a lot of focus because you have to trace a wire all the way around the design. Okay. And of course, with a spreadsheet, I can do something like this, but you cannot easily do it on a piece of paper. Well, you can kind of fold it and slide it and do whatever.
Very sorry, how did you do that?
Oh, okay. Before I did this, it looks like this, okay? There's a little bar here, right here. So when your mouse cursor turns into a double-sided arrow like this, you can drag it down, and you basically
you're separating the string into two panes. Now these two panes are still connected when you do a horizontal scroll. So horizontal scroll will scroll everything synchronized. But now you can scroll the bottom half independent to the upper half vertically. So that's really nice because I can now easily line up your stuff down at the bottom without changing the top.
Saving on the screen.
Frozen.
Yep.
You can use a frozen.
Thanks for coming.
Well, that's why you need to take a spreadsheet class before this one. I should make that a prerequisite to
Well, we took
programming.
300, would you argue if we wouldn't have that?
Well, there are all kinds of nifty stuff you can do. All right, so what we'll do is we're gonna, and you can print out here what I have already. In other words, if you think it might be helpful to know all the existing instructions, include that on a sheet of paper and bring it to class. Okay, bring it to the exam. Okay, because hey, open book, open notes, anything that's handwritten or printed prior to the test, that counts. Okay.
So just without a computer, we can bring.
You
anything.
cannot use anything electronic during the test. Well, hearing aid is okay.
iPad.
Huh?
A calculator, yeah.
I will bring a whole bunch of inexpensive calculators, but if you have a scientific calculator, go ahead. I really doubt any one of these calculators can run LogicSim.
Don't do that.
We will have one. We will
Well, my
develop
calculator may
one.
not be able to run LogicSim, but it can run a VNC session to a
Let's
PC that
develop
can
one.
actually run. Now I have to bring in my RF jammer.
Oh, wait, hold on.
All right, so let's go ahead and focus on this instruction. It is basically a STINDIR, store indirect with a register. Okay, so the first clock cycle, as I said, is to set up the indirect register so that the indirect register will drive the address bus of the RAM. Okay, so that's what we need to do first. So you basically have to go through all of these stuff here and say, okay, ALU really doesn't matter in this case. MCC clear, definitely don't want to actuate in here because that's what you do at the last instruction. Register 1 enable, yes, we want that, okay? Because register 1 is the one that can drive the data bus to RAM, okay? And it's okay to drive it here. Turn this to a 0 because it's not actually useful. We are not overwriting any registers. Indirect register write enable, definitely a 0 because it's already initialized. We don't want to change it. RAM select, you can go ahead and select it now. It doesn't matter. MCC increment / increment, definitely go for just increment because we don't want to go anywhere else based on the MCC, the microcode counter. RAM address PC / indirect, we want to select a 0 here because we want to complete the path so that the indirect register will be driving the address bus to the RAM. Okay. These bits are not used. Okay, there's one empty bit here that is not used. RAM read or write, it is definitely a read operation. We are not trying. Whoops, take it back. We are trying to overwrite the location. ALU out enable is a 0 because we are not using the ALU at all. Yep.
Wait, are we writing the content of the register to the address point to?
I'm using, okay, if I equate that to somewhat C type of code, I'm doing something somewhat like this. I'm using RAM kind of as an array. The indirect register is my index, and the content is whatever register that you specify using the YY bit in the instruction. So this can be register A, B, C, or D, depending on which one you pick. So that's kind of what I'm planning to do. All right. The indirect register write enable, or instruction, excuse me, this is instruction write enable is definitely a 0. We are not fetching another instruction here. PC write enable, we are not changing the program counter, put a 0 here. PC select increment, since we are not overwriting it doesn't really matter which one we pick, so we just put a 0 here. So that's my first microcode instruction. So once this is all set up, this bit pattern is going to be presented on a falling edge of the clock. Okay, so when the clock CLK is going from 1 to 0, these bit patterns will be specified onto the various components inside the processor. Okay, which means everything is going to be all set up because I would have completed the pathway from the indirect register to drive the data to drive the address bus. I would have completed the data path as well using register output 1 from the register bank to drive the data bus to RAM. Okay, and then when you have a falling clock or when you have a falling edge, the next one is going to be the rising edge, right? The rising edge is shared system-wide. And because I set up the RAM already to do everything, so the rising edge is going to overwrite the content in RAM. And then the next falling edge is going to move forward to the next, to execute the next microcode. So the next clock, or whatever I specify here on row 24, is going to be the last microcode. I'm ready to reset everything and go back and fetch the next instruction. Okay, so we'll go ahead and test it. Finish this, and then we'll go ahead and test it. Okay, so we can put a 0 here. Output, from the ALU is not important. We have to make sure that this one is a 1 because we definitely want to clear the microcode counter. We can turn off, all the output enable and write enable. Turn all of these off. RAM select, we can turn it off because the fetch cycle will turn it back on again by itself. Microcode increment, load, increment. We want to definitely do it. No, doesn't matter because it will, since it's going to be cleared, it doesn't really matter. RAM address going from PC or indirect register. We just put a 1 here, but it's not needed because the fetch cycle will reset this one anyway. RAM read or write.
If we put a 0 there, will that some else?
It would, yeah, it will still work.
Okay.
Yeah. RAM read or write. We just to be safe, we put a 1 here just so that we don't put the RAM module into a write cycle. ALU out enable, put a 0 here. We are not overwriting the instruction register yet. PC write enable, put a 0 here. And PC select, is it incrementing or is it coming from the RAM data? We'll just select increment. It doesn't really matter because the fetch cycle will overwrite it anyway. Okay, so these are the 2 microcode that we need in order to implement this little instruction here, store indirect. Okay? So the next thing we have to do is to do the bitwise conversion, which is kind of difficult at this point because we have to read everything kind of backwards. Okay, because this is the most significant bit. These are the least significant bits. I can still do it, but you have to read it kind of funny because this becomes 1. Okay, the first instruction is 0, 0, 0, 0. Okay, so that's the least significant bit. But when you work on these bits, you have to start from the least significant bit end and work your way to the most significant bit end.
I'm just saying that you could easily
flip it. Yeah. So we have, I'm just going to use this space here for that, okay? So the least significant digit in hexadecimal is going to be a 0. And as I said, it might be helpful to draw a border between the 4-bit boundaries. So one way to do it is to do it this way. And where's my border tool? Yep, there we go. And then you can add a border to the left. And it's not doing that.
Are you just adding border to that one cell?
Hmm?
Are you adding a border just to that one cell?
Oh, it does. Yep. Okay, and then the next one's going to be at bit 7. Add another border, and then another one at bit 11. Add a border, and the next one's going to be at bit 15. Add another border. I mean, you guys can go all fancy, like color code and do all kinds of crazy stuff with it. This is enough for me, so I'm okay with this. So I'm going to move this 0 to, I'll just put it here. Okay, so the next 4 bits is actually read kind of backwards because this is actually 0, 0, 0, 0, 1 because I'm reading the bits backwards. So this is just 1 in hexadecimal. The next one, this bit is not being used, which means it can be a 1 or 0. I'll just put a 0 here. This is also 0, 0, 0, 1, which is also another 1. This is all 0. And this is the most significant bit, and it is a 0. Okay, so the microcode that I should put into ROM is going to be from left to right is 0, 0, 1, 1, 0. Okay, because I have to read everything backwards because of the orientation of which side is the least significant bit and which side is the most significant bit. So to put this into ROM is 0, 0, 1, 1, 0. That's the first microcode. And then the next one, which is this one here, is 1 and then followed by 3 zeros. So that would make an 8. Okay. And then we have all zeros here. This one is 0, 1, 0, 0, which is a 4. This is 0, 0, 0, 1, which is just a 1, and this is just a 1 here. So the way you read it, once again, is backwards, and it is 1, 1, 4, 0, 8 as my second.
And then we all know that.
Yeah, that's kind of like a default, as the last microcode for a microcode sequence. All right. So that's the answer to the question. So if I am only going to work on this on paper, everything that I did earlier, okay, can be done on paper because I'm just using the spreadsheet more or less as a documentation tool, and I'm not using any type of automated calculation thing. Yep.
How you get the 4 too?
How do I get the what?
4.
The 4? The 4 comes from these 4 bits. So that is read as 0, 1, 0, 0, which is 4 in hexadecimal. Yep.
How are we going to put this like a 90? If we go from the last set, which is the most significant, can we go last 4, which is 0, 0, 0, 1?
Well, the bits are this row clearly indicates which bits we are talking about. Bit 0 to bit 2 is here. Bit 3 is here. So the rest is up to you. I mean,
And the 16, which is a 1.
This is bit 16. Yeah, it is a 1, but that's the most significant bit. When you group the bits into chunks of 4, you have to start from the least significant bits. All right. Any questions about this? So as far as the test is concerned, I have just answered my own question. Whether it works or not is a different thing. So we're going to test it, okay? So in order to test this, I will go to my simulator, and what we'll do is we are not going to input an entire program here because that would just kind of take too much time. Instead, I'll go to the ROM content. I'll just go ahead and fix this one to be 11500. Okay, which is not necessary, but I'm doing it anyway. And then at location 80, I'm going to program in the 2 microcode that we have just talked about, which is 00110 for the first one, and it's 11408 for the second one. So now the ROM or the microcode is programmed. It is time to specify an actual instruction, do some doctoring of register content, and test it out. Okay. So what I want to do, is to test this out with, say, register B. Okay, so it's not just register A. So we go to the RAM content in this case and specify the actual program. The instruction starts with an 8 because of 1000 being the most significant 4 bits. If I want register B, that means I have to specify 01 for the register, but this is register 1 because register 1 is the only one that can hook up to the data bus of RAM. The other 2 doesn't really matter. Okay, I can put 00 here, 11 here, it doesn't matter. Assuming I put 00 here, this is just a 4. Okay, because 0100 is 4 in hexadecimal, just like in decimal too. So the instruction is 8-4 to copy whatever is in register B to memory content, but the memory content is pointed to by the indirect register. Are we still doing okay? Well, obviously I have not loaded up anything yet. Okay. In other words, the indirect register is empty, and the way it's set up right now, I'm just going to overwrite location 0 with 0, 0. Do you guys want to see that happen? Self-modifying code, self-destruction code. But that's what's going to happen, right? I mean, it is important to understand what is going to happen if I don't do anything about it first. Okay. So what I'll do is I'm going to change it so it becomes a little bit more interesting. I go to indirect register, and just change this one to 0, 1, which is the next location. So I'm going to overwrite location 0, 1, and I go to the register bank, which is this guy here. And remember to switch to the hierarchical view first, so this way we can actually change the live content of RAM. And I'm going to change this to, we'll change it to 8-4. Now some of you are smiling because you know what this is going to do, right? Because what I'm doing is I'm changing the next instruction to be the same instruction as this instruction. But it will not overwrite location 0, 2 because there's no increment of the indirect register. So it's not going to self-propagate all the way through, okay, which would be kind of fun, but I don't have anything that can do that right now. Okay, so now that I go back to the main portion, I'm ready to simulate this code. But we know what it is supposed to do. Okay, what it is supposed to do is to overwrite this location in RAM with 8-4, because 8-4 is the content of register B at this point. Are we still doing okay? All right, so let's go ahead and clock it a few times and figure out what it's going to do. Let's zoom out just so that you can see the whole picture. The first 3 cycles are really just for fetching and decoding the instruction. And then we are going to continue execution at 8-0, which is right here. And you can see, at the first cycle, we are already changing the addressed location to the one that we want. And if you look at the data bus, which is here, it already has the content of what it is supposed to be. I know the font is really small. I can spell it out here. It is 1000, which is 8, 0100, which is 4. In other words, the address bus is all set up, the data bus is all set up. We're just waiting for a rising clock for the content to be programmed or to be written into RAM. So the next time I change the state of the clock, which is going from 0 to 1, which is a rising edge, it will change the content of this location, just like that, okay? And when I do another falling edge, it's going to move on to the next microcode, but the next microcode is going to reset the microcode counter, so I won't even see the next microcode here in this window because it will go straight back to location 0, 0 in ROM. And let's give it a try, and that's exactly what happened. Are we doing okay so far? Are there any questions about what I just did? So other than using the spreadsheet as a documentation tool so that I can help myself grouping all the bits together and actually not having to trace the wires in the schematic, everything that I did was basically on paper. Is that okay? Right. Now let's move on to the last question. I think nope, that's not the last one. We have a few more questions to go. Question number 5. In an 8-bit binary addition, the overall carry is set. Okay, in a particular addition, the overall carry, which is the output out of the entire ALU, is set. We know one of the numbers is 01101011 in base 2. What is the range of the other number, so the sum of these two numbers end up with the overall carry? Does everybody understand what this question is asking? Okay. Specify this range with 2 inclusive ends. So tell me the starting point and the end of this particular range of values. Okay, that's what the question is asking. So how would you approach a question like that?
Convert to decimal first.
You can convert it to decimal first. Yes, that would not be a bad idea. You can also do it in the opposite way. You can do a binary subtraction. Okay. Okay. Let me show you guys what I mean by that. I'm going to use mouse pad for this. All right. So the problem that we have now is we know what one number looks like, which is this one here. So we are basically saying this number plus some unknown number here is going to end up having a carry, overall speaking. And I don't really care what these other bits look like. I just know that there's a carry. Is that okay? So my job is to figure out what is the other number that I'm adding to 0, 1, 1, 0, 1, 0, 1, 1 that triggers the final or the last carry bit. Okay? And excuse me, don't drink in the classroom, please. Especially if it's Mountain Dew. Because I know how much sugar is in that stuff.
Bounce off the walls.
Hmm?
Bounce off the walls.
Yeah, well, that's why I drink black coffee these days.
That's a big. That's a big.
You don't bounce off the wall.
Coffee is calming,
Drink
in a way,
water.
strangely. Okay, so the other way to do this is to basically say the first number that is going to overflow is going to end up with all zeros here,
1, 1, 1, 1, 0.
right? So what you can do now is to say, hey, instead of trying to figure out the other bit pattern, we can just do a subtraction instead. Is that making any sense? And this is not going to be a very hard one. This is going to be a quick subtraction. So I'll do the full subtraction with all the borrows and whatnot. So this is going to be a 1 with a borrow. And this ends up with a 1, 2. This is going to be a 1 with a borrow. It's going to be a 0. This is a 0. This is going to be a 1 with a borrow. This is going to be a 1 with a borrow. That's going to be a 0, 0, 1, borrow, 1, borrow, 0, 1, borrow, 0, 0, and that's going to be a 1. And we end up with a borrow here, but that's not important. Because what we really need is this number here. If we add this number to 0, 1, 1, 0, 1, 0, 1, 1, we will overflow the number. Okay? Now you can convert it into base 10 first, then it is basically 256 minus whatever 0, 1, 1, 0, 1, 0, 1, 1 is, and that is the bit pattern that will first overflow the number, or it will first trigger the extra carry. Yep.
So is that's the minimum number
Correct.
to overflow? It could be anything above.
Yeah, anything above that will also do the same thing, and then so it's going from this number all the way to 1, 1, 1, 1, 1, 1, 1, 1.
Got it. Okay.
So that would be the range of values.
Can we just use a 1, 1, 1, 1, all the one?
Hmm?
No, you say well, you can't go all the way to the max because you have to. There's a number before that because clearly the max number added to some other number will clearly overflow, but there's some number before that that will reach that also.
Right.
So
So when you look at this, this particular value that's 9 times 16 plus 5. So that makes it what? I'm bad with
149.
arithmetic.
149.
Huh?
149.
149. And the other one, which is 1111, 1111, is 256. 255, sorry, 255. So the range of numbers is 149 to 255 in base 10. But if you give me binary numbers, and you specify it is in base 2, that's just as good. So it's kind of up to you guys to decide how you want to get to the answer.
So we have to specify.
255 and binary can be the right answer as well.
Yeah, if you specify 1111, 1111, and then you have a little 2 to indicate that's a base 2 number, that's fine too. Base 10 numbers do not need any indication because that's kind of the default. Hexadecimal numbers start with 0x.
How can we do?
Now, just to double check, okay? You know, I hate to make mistakes, so we'll double check and make sure that this works out. This is 6 times 16 plus that would make 11. That's 96 plus 11, 107, right?
Yes.
Okay. If you add 107 to 149, you should get 256. That seems to work out too. So I'm just cross-checking my math, okay? Because if I made a mistake, it would not, or unlikely to add up to 256. Yep.
So you want the answer to be that number that'll initially push it over, and then whatever the maximum
Right.
number.
Yep.
So it's just kind of like right at the interval.
Yep. Yeah. I think in the question it just says, give me those two numbers, inclusive ends. And you don't have to specify in a sorted way. If you specify 255 and then the other number, that's fine. Yep.
It looks like just the inverse of the previous binary plus an extra 1 to push it over the edge.
Exactly. And that turns out to have some interesting property. Inverting the bits, add 1 to it. We'll see whether we have a chance to get to that one.
It's not yet, that's a two's complement.
Two's complement, exactly. So that's question number 5.
1, 0, 0, 1. Then add 10.
Okay, question number 6 is to draw a picture of a 6-bit adder using full adders. Clearly label the pins of each component. Use it to compute 17 plus 50, that's in base 10 because it doesn't indicate the actual base. Label all the wires to indicate whether each wire has a 0 or 1. Okay, so for this one, it's probably easy to just to draw it on the whiteboard. Okay. So, full adders, right? It's a 6-bit adder, so we have 6 of these things.
Okay. I thought we had to draw the underneath.
The underneath?
Like, how we, like the very first question we were in action just show the notch with the XOR gates. I thought you meant you wanted us to.
Oh, no. Just the overall picture. I wouldn't want you guys to have to draw all that stuff. Okay, so 0 goes into the carry of the first one, the least significant bit, and then from that it's just propagating all the way through. And this is the last one. Then we have 2 input bits, and because this is an addition, it doesn't really matter which way you want to specify because it's symmetric. So we have 2 input bits. Okay, the first number is 17. 17 is, have a 1 here, 0, 0, 0, a 1 here, and another 0 here. That's 17. This is 1, 2, 4, 8, 16, 32. Okay, the other number is 50. So 50 has, well, we can work backwards, right?
So we got
132.
we got
That will
16.
make it
16 will be a 48.
yeah, so 132,
And then a 2.
116, and then we have 1, 2, and 1, 1. 0 goes here. Okay. So that's what I mean by labeling.
No, we
no,
said 50
there's
because
no 1.
yeah, there can't be a 1 at the 1
Yeah.
spot. It's an even number.
It's an even number, yeah.
Oh.
30.
There you go. All right, so I want to label every single wire here with a 0 or 1, okay? Because I want to know the state of the entire thing. So even if your scientific calculator has a way to do binary addition, it will only give you a part of the answer. It won't give you everything in between, right? Okay, so this is that's a 1 with 0 as a borrow. That's a 1 with 0 as a borrow. That's a 0 with 0 as a carry. Kept saying borrow. 0 with no carry. This is a 0 with a carry. This one is a 0 with a carry. So that's the whole picture.
So that's the whole picture.
Yep, that's the entire picture. All the wires are labeled.
Do we have to label which number is which?
Not for this one because it's an adder. If it's a subtractor, then we have to kind of label which one is being subtracted from which one. All right. So those are all the questions. So you have the weekend to study and get ready for the exam. If you have any questions, you can bring those questions on Tuesday and we can talk about it in class. If there are no further questions about, yes?
There's no question 7?
There's no question 7, yes. There's no question number 7 in the practice exam, I should say.
So we have some more.
Possibly. All right, so with no other additional questions, we're going to move on to signed numbers, which is really fun. We are allocated 4.5 hours to talk about signed numbers. We won't need that. However, we also have to talk about the other flags, including the sign flag and the overflow flag, and how to compare numbers. And that will take up some time, okay? All right, so first thing first, what is a signed number? Okay. When we look at a certain bit pattern, let's just pick a 4-bit pattern here. 1 0 1 1. Okay, we know what this is. As a binary number, we have 1 1, 1 2, 0 4, and 1 8. So this is really representing 11 in base 10. Okay, that's something that we should know already. But if this is the only way to interpret a bit pattern, that means we have no way to represent negative numbers. Well, I guess in real life we do have to deal with negative numbers, so we better have a way to represent negative numbers. So now the question is, how are we going to represent negative numbers? Now, the most common, first attempt to represent negative numbers is to say, well, we can just use 1 bit as a sign bit, and if that bit is a 1, the value is negative. If that bit is a 0, it is a non-negative number. Well, that's not really bad as a first attempt, but doing things that way means you have to have specialized adders and specialized subtractors, because your normal adder and subtractor won't be able to handle it. Okay? So what we do is we use 2's complement to negate the value of a number. Okay? It's all in the notes. I put some extra links here. Some of those links have been around, but I included some extra links, so you should probably be reading some of those links too. Okay. But we have a special way to do negation. Okay. Now in arithmetics, when you take a negation of x, it is basically the same thing as 0 minus that particular value. Okay. We know that. That's nothing new. So that's just -8. Okay, the negation of 8 is -8, and if you take double negation, you get the original value back. Okay, nothing big, nothing surprising here. When you're dealing with 2's complement, we are actually going to get the same results. That's the whole objective, is we want to get the same result using 2's complement. So 2's complement looks like this. I'll use C2 to mean 2's complement. So when you take the 2's complement of some bit pattern, okay, I'll just say x here, you're basically doing a first 1's complement of x, and then you're adding 1 to it. Now 1's complement, to those of us who remember our C operators, is bitwise not. That's all it is. Bitwise not also has a name of 1's complement. Now, bitwise not, as the name implies, is really just flipping all the 0s to 1s and all the 1s back to 0s. Okay, so your observation earlier definitely has a point here. Okay, so I'm claiming taking a bitwise not plus 1 is the same thing, which is now called 2's complement together as an operation. It's called 2's complement. So what I'm claiming is it's the same thing as negation. What do you mean by the same thing as negation? Well, I mean it has the same properties as arithmetic negation. Okay? One thing you can do, or I can try, is to do it like this. Okay? If you want to say, A minus B, okay, using subtraction, I can turn this around a little bit and say, let's do this instead. A plus the negation of B. That should come up to be the same answer, right? So if I claim that 2's complement is doing negation, and we already know how to do bitwise subtraction, we can now test it to see whether it works or not. Now, this is not a formal mathematical proof, but it is enough to kind of convince most people that then say, oh, okay, I can see they're pretty much doing the same thing. So let's go ahead and test this, and I will let you guys pick the numbers that we're dealing with here, as long as they fall into a particular range, it should work. Okay? So give me an A and a B, both non-negative, and I'll use this method to come up with the difference between those two numbers. Yeah, you can even pick a B that is larger than an A, so we end up with a quote-unquote negative number, because that way I can show you what a negative number would look like and how to find out the magnitude of the negative number.
So what I'm saying is, do you want the bit vector?
Let's do with 4 bits. So we're dealing with numbers that are from 0 to 7.
3 and 5.
No.
He's fast. 3 and 5. Okay, so A equals 3, B equals 5. So we'll give it a try. Okay. So the first way is to do it using the usual subtraction method. Subtraction method means we are using 0, 1, 0, 0, 1, 1 minus 0, 1, 0, 1, and 1 minus 1 is a 0 with no borrow. 0 minus 0 is a 0. That's a 1, and since we don't have any borrow from before, that's a 1. This is a 1. Now we have a borrow, and now we have 0, and this is going to be a 1 with an extra borrow. Okay, but when we are dealing with a 4-bit subtractor, this, even though it has some value later on, this is the result. Okay, so this is the actual result of a 4-bit subtraction. Okay, so we know what it looks like using a regular subtraction thing. Now we'll do it the other way. In other words, we'll first figure out what is the 2's complement of 0, 1, 0, 1, and then we'll use regular addition to add up the bits. Okay? All right. So the 2's complement of 0, 1, 0, 1 as a 4-bit number is the negation, bitwise not, the bitwise not of 0, 1, 0, 1 in base 2 plus 1. Negation or bitwise not is easy. You flip all the 0s to 1s, all the 1s to 0s. So it becomes 1, 0, 1, 0 in base 2 plus 1, which is 1, 0, 1, 1 in base 2. That doesn't look like 5 to me.
It's different.
Doesn't seem even close to a 5 to me. Okay, but I'm claiming this is actually 5. Okay, so the next step is to perform a regular addition, 0, 0, 1, 1, which is our 5, and I claim that this is doing the same thing as negative 5. Okay, so let's give it a try, right? 1, 0, 1, 1. 1 plus 1 is a 0 with a carry. 1 plus 1 is 0 with a carry. 0 plus 1 is a 1. 0 plus 0 is a 0. 0 plus 1 is a 1 with no carry. 0 plus 1 is a 1. 1 plus 0 is a 1. Okay. They come up with the same bit pattern. 1, 1, 1, 0 turns out to be the same, the result of both operations. One using the usual subtractor that we have already used many times. The other one is using the 2's complement to figure out what is the representation of negative 5, and then we perform a regular bitwise addition to come up with the answer. But they come up to be the same. Okay, so what exactly is this number? It doesn't look like
the absolute value.
Let's try to find out the absolute value. So now the first question is, how do we know this is a non-negative number or a negative number? As it turns out, if you use 2's complement to get to your negation, this is the most significant bit is the sign bit. Okay, if it is a 1, it means it is representing a negative value. So if this is a negative value, I want to know the magnitude of this negative value. How do I find the magnitude of a value that is already known to be negative? You can take the negation of it, right? And how do we do negation again? 2's complement. Okay. So we will now apply 2's complement to 1, 1, 1, 0 as a 4-bit number, which is the bitwise not of 1, 1, 1, 0 plus 1. The bitwise not of 1, 1, 1, 0 is 0, 0, 0, 1, right? Add 1 to it, it becomes 0, 0, 1, 0, which is 2. Okay, so the negation of 1, 1, 1, 0 is 2. That means 1, 1, 1, 0 is representing what?
-2.
-2. Yep. So it all works out. Okay. Now, if you want to kind of understand why we have to go through this kind of strange, operation called 2's complement to represent negative values, it is easy, because with this way to represent negative values, we can just add just like usual. We can subtract just like usual. Whether a number is signed or not does not change how we add or subtract whatsoever. Go ahead.
I don't know if this will help, but I always found it easy, like, to get that number. You would take it like that was a regular unsigned bit vector, then you would just do your regular, like, that's 2 to the power of 3, and then you add those up. But in a signed number, that's going to be 2, like it's going to be a negative, so that's actually negative A, and then you add, then the rest is just added, and you'll get back to that number.
That is correct. That's one way to look at it too. But there's another thing that you should probably look at, because the main confusion point is now, okay, so what the heck is 1, 1, 1, 0? Is it -2 or is it 14? Right? Because it can be 14 too. It is 2 plus 4 plus 8, which is 14. So which one is it?
It just depends.
Exactly. It depends on a lot of things. It is both, actually, at the same time. Okay? The adder doesn't care, the subtractor doesn't care. It is just a bit pattern, and it works out either way. Now, before we end today's class, I want to give you one thing, and it is called a number circle. I'm pretty sure most of you have seen a number line, right? But in actual computer science, in actual programming, we don't deal with a number line. Why is a number line a nice thing to have, but we cannot have it in programming?
We have discrete stuff.
How many bits do you have in a computer? A lot. My computer has 16 gigs of RAM. Well, 16 gigs of RAM is still a finite number, right? With a finite number of bits, you can only represent numbers up to a certain range, and then you wrap around, right? And that's why in computer science, we look at numbers not as a number line, but as a number circle, okay? Now, with 4 bits, obviously, this is a really small circle. But if you have 32 bits or 64-bit, it simply means the circle is much bigger. But the principle does not change. All right, so we look at a circle like this, and then we chop it up, or we basically insert all these points. There are 16 points on this circle, because with 4 bits, I have 16 unique bits, bit combinations. Okay, so let's say this is 0, 0, 0, 0. I'm just going to fill in like a few, just so that we know all the important parts, okay? And if you continue this way, this becomes 1, 1, 1, okay? So this is how we allocate, all the bits, all the combinations of the bits. The normal way to interpret a bit pattern, which is, this is a 1, this is a 2, this is a 4, and this is an 8, will be pretty easy to deal with, because that means this is just representing the value of 0. Value of 1, 2, 3, 4, 5, 6, 7. Okay? But then we look at this one and say, so what is it? Is it 8, 9, 10, blah, 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 all the way up to 15? Or should we go the other way? Because 1 minus 1 is 0, right? 0 minus 1 is -1, -1 minus 1 is -2, and so on. And then it becomes -7, and this is -8. So that means we have to somehow, some of these things have 2 values that they can represent, half of the wheel. And the reason why we only have up to 7 here is because this is using up half the values already. And that's because 0 is using up 1 space. So that's why for non-negative values, it only goes up to 7. Okay. All right. So with all this discussion, the one thing that has not changed is when you rotate the wheel counterclockwise, we are increasing. So imagine there's a marker here, that does not change. Instead, you're changing you're rotating the wheel itself. If you're rotating the wheel in a counterclockwise way, we are increasing. When you're flipping it the other way, it is decreasing. And that's why your two's complement is really nice, because it preserves the direction, which way is increasing and which way is decreasing. And that's also why we don't have to change the way that we add or subtract when we have representation of negative numbers using two's complement.
And you also don't get a negative zero.
And you also do not have double representation of zero, which is a waste of bit patterns. Yep.
Can you explain again why only half of the circle has can represent two numbers? Like only 1, 1, 1, 1, and it can be 15 or negative 1.
Well,
but 0, 0, 0, 1 can only be 1.
Don't get rid of the 15, it's just confusing.
Because you don't want zero to have multiple representations.
I mean 1.
Yeah, or one. You want one whether you have signed numbers or unsigned.
It's because, right, because if you want to also represent negative values, and we're using two's complements to represent negative values, then we are looking at the most significant bit as a sign bit.
Okay.
That means, this is a bit, this is a representation of the negative value.
Okay.
When you look at it the other way. Okay, but the main confusion point now is, now that we know that certain bit patterns can be either representing a negative value or a positive value, when does it start to matter? Okay? Now, think about in your C and C++ programs, the type int and unsigned int. Okay, those two are the ones that can differentiate. Is it a signed number that can represent negative values, or is it an unsigned number that can only represent non-negative values? Okay, when does it matter? When
If you need negative numbers. If you need negative numbers.
When you need negative numbers, okay. But when does it really, matter whether it is a signed number or not? Okay. In other words, let's say I and J are signed integers. Okay? I plus equal to J. Does it matter whether it's signed or not? No, you just go through the regular adding logic and store whatever the result is in I, right? Signed or unsigned is the same operation. So when does it really matter?
Subtract.
Comparison. When you compare numbers, then it matters a lot, right? Because when you compare a number, that is the only time when you have to figure out the ordering of what the values are being represented by the bit patterns, okay? And that depends on whether you're dealing with signed or unsigned numbers. In other words, if you're dealing with signed comparison, 1, 1, 1, 1 is representing a value that is less than 0, 0, 0, 0 because it's negative 1. This is signed. If you use an unsigned interpretation, guess what? It's the other way around. 1, 1, 1, 1 is representing a value that is greater than the value represented by 0, 0, 0, 0. That is when things are important, whether it's signed or not. Okay? So typically, where do you have I is less than J or something along this line in a C or C++ program? Would you do this like all by itself with a semicolon? Well, it is actually valid C syntax, okay? But it doesn't do anything that is particularly useful, right? So when do you use I is less than J or something like that? A conditional statement or loop, okay? So to be more specific, if you just look at this expression here, how is it usually treated in a programming language? It's not even limited to C or C++.
As a true, false.
It's a condition, true, false, okay? It's something that will let you decide, well, should I go here or should I go there? Okay? It is at a branch that it matters, okay? And it's the same thing in assembly language programming. Whether a number, a bit representation, is signed or not, doesn't make any difference whether you're adding or subtracting. It only matters, it doesn't even matter when you're comparing. It is only mattering when you're using the result of comparison to choose which way to go. Okay, so I'm going to stop here you might want to read the notes because everything that I talked about today about signed number representation is here. So that is kind of important.
That's a lot easier to write.
Really?
This is just numbers. Yeah, this is just numbers.
I don't know about that. Okay, so the assignment, which is add flags to the ALU, is not going to be assigned. So forget about this homework assignment. I'm giving people more time to finish the current homework assignment. But if you want to go ahead and do this one, go ahead and play with it, okay? Because it's not really that hard.
So that assignment's not going to be required for. That assignment's not going to be required or accounted for.
It does not have a due date yet. So it is up. Yeah, it is up. If you want to do it, if you want to do it, go ahead. But it's not, it's not officially assigned just yet.
Okay.